The theory of relativity is used to account for observations from different perspectives.
For
For example, objects appear to be smaller when they are viewed from a distance. Additionally, motion is relative to the perspective of the observer, as objects in a car appear to be still from the perspective of within the car. What about time? Is time an absolute value, or does time change depending on how we look at it? In other words, is a second the same for every observer, regardless of their perspective? Well, as it turns out, the answer to this question is no. Rather, time is relative. Time slows down for objects approaching the speed of light. In the 1970s, scientists did an experiment on the effect of speed on time. They put atomic clocks on fast-moving planes and had them fly around the Earth twice. When compared with the same atomic clocks sitting on Earth, the clocks on the planes slowed down. In other words, not as much time had passed on the planes. Once again, time slows down when you're going really fast, close to the speed of light. Humans have not come anywhere close to approaching the speed of light, so we have not had the opportunity to experience this phenomenon directly. How can time slow down at really fast speeds? Well, to answer this question, we need to consider how we measure time. Time is measured by the observation of repeating events. All clocks record time with some repeating event, such as a pendulum moving back and forth in a grandfather clock. More sophisticated clocks use light beams bouncing between two mirrors as the repeating event to measure time. Each time the light bounces off the mirror, the clock ticks. Because light maintains the same speed, you don't have to wind up this clock, it keeps on ticking. As long as your clock is not moving, the light will move the same distance between the mirrors with each pass. However, if the clock moves, the beam of light will travel a greater distance with each pass between the mirrors. If we accept that each pass of light between the mirrors is the same unit of time, a second, for example, then the same unit of time now takes longer to pass when the clock is in motion. In other words, time slows down. This slowing of time at high speeds is referred to as time dilation. It is important to note that time dilation is relative to the perspective of the observer. In other words, if you were to travel in the spaceship with the clock, you would notice no time dilation. Everything would seem normal to you. From your perspective, the beams of light would be traveling back and forth between the mirrors just as if you were sitting still. However, from a stationary perspective, time slows down. In other words, only the stationary observer observes time dilation in the moving ship. Time dilation helps explain how the speed of light doesn't change with perspective. The speed of light is abbreviated by the letter c, and it's approximately 300,000 kilometers per second. That's pretty fast. Whether the observer is moving at speeds close to the speed of light or stationary, the speed of light is always measured as c. To explain how this works, let's look at an example. Imagine you are positioned on Earth and you observe two spaceships. One ship is not moving relative to the Earth, while the other is traveling close to the speed of light, let's say 250,000 kilometers per second. If each ship fires a laser of light, how fast would you record each laser of light? Let's start with the stationary ship. If you use your trusty radar gun, it would clock the laser at 300,000 kilometers per second. That is the speed of light. And that makes sense. But what about the speed of the light laser shot from the fast-moving ship? You might expect the laser to be traveling at a speed faster than c, that is faster than the speed of light. because it is already shot from a fast-moving ship. However, your trusty radar gun would clock its speed at 300,000 kilometers per second, just like it came from the stationary ship. While that might not make sense, it is correct. So don't throw away your radar gun. For that matter, the pilots of each ship would clock the speed of each light laser at the speed of light as well. How can this be? How can light travel at the same speed regardless of the light source or the observer's perspective? To answer this question, we must examine speed. Remember, speed is simply a measure of distance traveled over a period of time. So even though the observers agree that the speed of light is always c, they do not agree on time. According to the stationary observer, time has slowed down for the fast-moving ship. In other words, the passing of time slows down as objects speed up. The slowing of time at high speeds helps the observers agree on the speed of light. If time slows down as objects move faster, then why don't we notice it? Well, we don't notice time dilation in our everyday life because we don't come anywhere close to the speed of light. It is only at speeds close to light that time dilation becomes evident. In summary, time dilation occurs at high speeds, such as the speed of light. Time dilation is the slowing of the passage of time at high speeds. The faster the object moves, the greater the amount of time dilation. Time dilation, in part, accounts for the constant speed of light, regardless of the light source and regardless of the observer's perspective. If a fast-moving object emits a beam of light, the light still moves at c, that is 300,000 kilometers per second, the speed of light. This is the speed that would be observed by both the pilot of the spaceship and a stationary observer outside of the ship. As speed is a measure of distance traveled over time, the speed of light can remain constant if time is changed. Time dilation is negligible at speeds that we encounter on a daily basis. Time dilation becomes evident only at speeds approaching the speed of light.